So this third video is just the last type of calculations you're going to see before we get to limiting reagents and percent yield. So we left off on writing the balanced chemical equation of the decomposition of sodium nitrite. So now we're just going to see is if I go from mass to mole, how it's going to look a little different. So in this flip chart up here, if I kind of highlight where we went, we started up here on the flip chart with it being closed. We then went down to the grams to find grams. So now in this type 2 problem, now I'm actually giving you grams to start, which means we have grams of A, and then we're going to go up to find just moles of B, okay? So I give you the balanced chemical equation actually for this reaction, and I tell you that I have 250 grams of sodium chloride. So we know that that's given, which means I have grams of A. I want to know how many moles of chlorine gas will be produced. So I'm trying to find moles of B. So if I look down here at what I have highlighted, we're going to start with the grams of A. So my 250, you always start with the number given. And we convert that out of grams to moles, okay? So since grams are on the top now I need to divide by my molar mass to get me moles, which is what we did back in unit 8 with the mole. So if I take a sodium plus a chlorine, I get a molar mass of 58.44. So now that goes on the bottom because there's 58.44 grams of sodium chloride, just NaCl, in every 1 mole of NaCl. So that gets my grams of sodium chloride to cancel, which now I'm at that mole ratio part again. Okay, that's the most important part, is now I know my mole ratio between sodium chloride is a 2 to 1 ratio. So for every 2 moles of sodium chloride, I produce 1 mole of chlorine gas. So everything cancels except for my moles of chlorine, which is what I want. So in the calculator, you're going to take 250 times 1 times 1, which just means you're taking 250 and you're dividing that by the quantity of 58.44 times 2. So it's always the quantity of the denominator. So once you do that and you divide it out, you get a total of 2.1 moles of chlorine. And that's your answer. Okay. So now how useful is that really? Not. We can't actually measure out a mole easily in the lab. So this is where type 3 calculations are going to be most important. So obviously these ones are going to take the most number of steps, but they're going to be most useful, and these are the ones that you're going to really be using in the lab and in the practice problems and things that we'll be working through. So this chemical equation, I already give you the balanced equation. Stannous fluoride is used in toothpaste. It's made by reacting tin with hydrogen fluoride according to this equation. So first thing I want to talk about is just how we recognize A and B and really what part of the flip chart we're going to use here. So I want to know how many grams of SNF2. So if that's what I'm trying to find, that means I'm going to be finding grams of B are produced from 30 grams of HF with enough tin. So that means the other thing that I'm looking at here is 30 grams of HF, which means this is grams of A. So it's not that we don't care about the tin or the hydrogen, but we just are not going to need it in our calculation. Now, if I look at my flip chart, that means my flip chart's going to be completely open now. What I've just highlighted down here, are the number of steps I'm going to use. So I'm going to start with grams, I'm going to end with grams, which means I actually need the molar masses of both of these compounds. Now I'm going to save you a little time with this and go ahead and give you the molar masses, and in some of the problems that we're going to do, I'll have the molar masses embedded in here. So the molar mass of HF is 20.01 grams per mole, and the molar mass of SNF2 is 156.71 grams per mole. Okay? So we're just going to start with the number given in the problem, the 30 grams, and we're going to plug that in for grams of A. So again, you can plug in HF, or if you'd rather use A's and B's, that's completely up to you. So I'm going to start, if I look here at my flip chart, by just getting rid of the grams of A by dividing by its molar mass, which means I need to use the 20.01 grams here on the bottom. And that's for every 1 mole of HF. You never use the coefficients in front until you're ready for the mole ratio, this middle section. So anytime you have the molar mass, you always put 1 mole with it. Now, in front of HF is a 2. So if we look at that canceling, so for every 2 moles of the hydrogen fluoride, I produce 1 mole of SNF2. So that gets my moles of HF to cancel. Then I know that 1 mole of SNF2 is the molar mass of that, 156.71 grams of SNF2, which gets that to cancel. Okay? So mathematically, what do? I take 30 times 156.71 divided by 20.01 times 2. So that's what it should look like in your calculator. Now you should be close with sig figs here. So my initial number here has 3. So that means your final answer should have 3. I'll give you a second to calculate it. You can always pause the video if I'm going too quickly. So once you do that and calculate it, you should get 117 grams of SNF2. So practically speaking, they actually use this a lot in industry and drug development. If I say that this is how much I make, how close am I to actually making that amount? So that's where we're going to get into the percent yield and how good of a job are we actually doing in the lab. For right now, we just need to be able to calculate the theoretical amount that we should make. All right, so last 2 problems that we're going to look at here. Next one is milk of magnesia. So if you've ever had to take that, if you had an upset stomach, this is what you take if you have a lot of excess stomach acid. It's an acid-base reaction. It's telling you that reacts with stomach acid. So those are my 2 reactants. So we need to write a balanced chemical equation first. So I have this MgOH2, magnesium hydroxide, reacts with hydrochloric acid, and it produces magnesium chloride, MgCl2, plus you're left over with, anybody? You're left over with water. So any product of a neutralization is water and salt. Now, if we look at this, we should be able to notice that our equation is not balanced. You would need a 2 and a 2. Okay? So again, that's back when we did our chemical reactions. That part should be reviewed. So now it's telling you determine the mass in grams of magnesium chloride produced from 3 grams of magnesium hydroxide. So that really means that we're comparing both of the magnesium compounds as my A and B. I'm telling you that I am starting with 3.00 grams of magnesium hydroxide, which means we have grams of A there, and I want to know how many grams of magnesium chloride I should produce. So the other piece of information I need to know about both of these are the molar masses, which I will give you off beside these. So the molar mass of magnesium hydroxide is 58.32 grams per mole. So again, when you're doing these calculations, you can use molar mass calculators or just have a periodic table handy. And then 95.21 grams per mole is the molar mass of magnesium chloride. We don't need to see that. Okay. Oh no, it's going to crash again. Maybe not. No, okay, we're good. Okay. So I have all my values, so now I'm just going to plug them in to my flip chart. So I'm going to always start with the number given in the problem, the 3 grams of the magnesium hydroxide. I'm going to just label these ones A and B just so you can see how that works. All right, so the first thing I need to do is get rid of grams of A, which means I need to use the molar mass. So for every blank grams of A, I have 1 mole of A. So that's where I'm going to plug in the 58.32 because that's the molar mass of A. So that gets my grams of A to cancel. So once I get to moles of A, now I'm at that mole ratio part. So this is where I use the coefficients. If you notice in this balanced equation, they're both 1. So for every 1 mole of A, I produce 1 mole of B. Even though you recognize it's 1-to-1, it's very important to always show that. Showing more work is better than, it'll just help you keep track of what you have. And we crashed, so let's try it one more time. There we go. Okay, so then the last part here is for every 1 mole of B, I have my molar mass of 95.21 grams of B. All right, so that's going to get me grams of B. So if I just multiply across divided by 58.32 using 3 sig figs, that means I should produce 4.90 grams of B, and I would just switch that out with the actual compound, magnesium chloride. Okay. All right, so the last problem is a mixed unit problem. So if we look at this one is now saying how many liters of nitrogen gas are required to react with oxygen to form 30.2 grams of nitrogen dioxide, and this should say at STP. All right, so now we have liters. So basically the only thing that's different is now I'm starting with grams, so I'm still going to go from grams through the mole ratio, but now instead of going to grams of B, now I'm going to go to liters of B. And what we learned in the last unit, okay, I just have a little delay here, is that 1 mole of any gas always occupies 22.4 liters as long as you are at STP. Okay, so the first thing we're going to need to write with this equation, though, is your balanced chemical equation. So I'm telling you nitrogen's reacting with oxygen, which means N2 is being added to O2. Those are both diatomics to form nitrogen dioxide, which would just be NO2. So again, this equation is not balanced. I need a 2 in front of NO2, which means I also need a 2 in front of O2. Now that I have that, I can figure out where I'm going. So I start with the 30 grams of nitrogen dioxide. That's what's given, which means we have grams of A. I want to know how many liters of nitrogen, so that's going to be liters of B. Okay, so we're going to start with our 30.2 grams of the nitrogen dioxide. I'll call that A again. So what I need to know about nitrogen dioxide is the molar mass. And if I take 2 oxygens, which is 32, and a nitrogen, which is 14.01, I get 46.01 grams per mole. That's just the molar mass of that compound. That gets me to moles of A. Once I have that, now I use my mole ratio. So for every 2 moles of A, because there's a 2 out in front of NO2, I need 1 mole of B. Now, instead of going to grams like the last 2 problems, now I know that 1 mole of B, or that 1 mole of gas, occupies 22.4 liters. So the only thing that we're changing here in this problem is that we're using 22.4 instead of the molar mass. So the math is the same. I would multiply 30.2 times 22.4 divided by the quantity. And with 3 sig figs, I would get my final answer, use a different color here, to be 7.35 liters of N2. So those are the basic calculations using the variety of different ways with the flip chart. Please let me know if you have any questions. And then the last video, I'll be explaining more of the limiting reagents and percent yield.